Again, I would like to honor Professor Bran Wayele, who was my supervisor during my master's degree study at Stellenbosch University in South Africa. He was a dedicated mentor, brilliant statistician, and inspiring researcher. And his guidance shaped this work. His legacy continues in the field of biostatistics. So these are the outline of my presentation. So data collection often encounters incomplete information due to various factors, especially in HIV survey research. Missing data is inevitable, and it is a common issue. So one of the reason is non-participation in an HIV test because of absenteeism or refusal to be tested, and which can create several associated factors. And one of the main reason for a subject to refuse HIV testing is their HIV status knowledge. So in this context, missing data complicates analysis. Not only loss of power, it also introduces bias when the reason for the missing data is related to the scientific question we are interested in. In HIV survey research, survey weight is one of an important variables in the data set, which is used to adjust for unequal probabilities of selection, non-response, and coverage issues. Several methods has been developed to deal with missing data in different contexts, assuming several assumptions. So one of the biggest categories of missing data methods is represented by imputation strategies. Imputing missing data means replacing the missing information with a single or several values. So the missing data mechanisms define the distribution of missing data given the underlying data. Suppose in the given data set, if we represent the observed information by Y observed and the missing information by Y missing. So for each variables in the data set, we can have observed values and the missing values. So we can generate an indicator variable Mij for the ith individual in J's enumeration area. 1 if Yij is missing, 0 if Yij is observed. So based on this, there are 3 missing data mechanisms. One is missing completely at random. This is when the probability of missing given Y does not depend on both observed and missing information. Missing at random is when the probability of the missingness given Y only depends on the observed information. Missing not at random mechanism is when the probability of missingness given Y depends on both observed and missing information. And the third one is, which is very complex and complicated. Okay, so there are different approaches to handle missing data in HIV studies. So the first 4 are the most commonly used methods, even in some other settings. Complete case analysis, where we only use complete cases in order to estimate the parameter of interest. This is valid under the strongest missing completely at random assumption. The other approach is inverse probability weighting, where we model the missingness first, then we predict the probability, then we take the inverse of that probability to take into account the missing information for the final inference, which is valid under missing at random. But this approach requires the correct specification of the missingness model. So with the incorrectly specified missingness model, we end up with invalid inference under using this approach. The other method is consent to HIV-adjusted inverse probability weighting. So in this case, we model HIV testing non-response, and then we calculate the inverse probability weighting to account for the missing information. The other approach is standard multiple imputation, which is a common techniques and a well-known method of handling missing data in different settings. The assumption is the probability of missingness depends on observed data. Uh, since the regression model we use in standard multiple imputation is not the weighted regression model, this approach does not account for survey weights, particularly in HIV survey research. So I will be mainly focusing on an alternative approach which is robust, which can take into account the survey weight uh, in handling missing data, and then for the final inference as well, which is called heteroscedastic multi-level multiple imputation. So in missing data, in multiple imputation in general, the missing values are imputed from the Bayesian predictive distribution of the missing data given the observed data, so that we can have several imputed data sets. We then use a model for the intended model for the final inference to find the estimates for the K imputed data set. And then for the final inference, we can use Rubin's rule in order to pool the estimates from different data sets. So with an HIV survey research, the issue is now the variance of the Rubin's variance can no longer be unbiased if we do not take into account the survey weight in both imputation and the substantive model. So the objective of this project is handling missing data in HIV surveys with survey weights to predict HIV prevalence and identify factors associated with HIV status. We used the 2016 Ethiopian Demographic Health Survey data for this project. Suppose the substantive model is a weighted regression model, which is common in survey sampling settings. And in this case, appropriate weighting is often used to take account of the sampling schemes. In practice, the key issue is whether we have the correctly specified imputation model or not. So one possible approach is to impute separately in each weight strata, so that the relationship between the variables are allowed to differ across weight strata. Or the other approach is to include the weight variable as a factor variable, possibly with interactions with other variables and in this linear form. Now we have a large number of parameters to be estimated, which will make estimation noisy. So the better option under heteroscedastic multi-level multiple imputation could be using the weight variable to define a second level in the data set, then adopt a multi-level approach. So including the weights in the space spanned by the variables in the regression model can give us unbiased Rubin's variance in this context. We can also pull information across weight groups where appropriate, and this approach performs well even if the proportion of missing in some weight strata is high. In the case of the 2016 Ethiopian Demographic Health Survey data, our primary variable of interest is the HIV status, which is actually binary. And given now the random effects in the context of heteroscedastic multi-level multiple imputation, the observed response follows Bernoulli distribution, and the log also of this probability can be modeled using a mixed effects logistic regression. So in our data says the missingness in the outcome of interest was about 8%. That HIV prevalence was 6 times higher in urban than rural areas. HIV prevalence was higher for women with primary education compared to the women with no education. The risk is high for women in the higher age group compared to the women in the lower age group. Age, place of residence, religion, region, and educational level are factors significantly associated with HIV status. So this is a result after imputing the missing information using the 5 different approaches, including the one which accounts for the survey weights as well. So we fitted using different methods, checking the missingness assumption for each approaches. And in most of the cases, in terms of the significant variables, the effect size and so forth, relatively more or less the results seems the same. And finally, we also predicted HIV prevalence using the 5 approaches. And we also included the one reported by Ethiopian Statistical Service, and in theory and with using preliminary simulation studies, heteroscedastic multi-level multiple imputation is robust compared to the other approaches in terms of bias, coverage probability, confidence width, and the root mean square error. So we assume the other approach underestimated the the overall HIV prevalence using the data of 2016 Ethiopian demographic health surveys, because almost the other approach does not take into account the survey weights. And in the case of, for example, inverse probability weighting, if the imputation model is misspecified, with this approach, we can end up with invalid inferences. Okay, in this project, we used several methods to handle missing data in HIV studies, and we compared with the approach which can take into account the survey weights. Accounting for weights in both imputation and the substantive models for valid inference is very important. With high dimensional data, incorporating all domains with their interaction might be complicated and may need an advanced technique in this context. So plan for future work is comparing the results with other alternative multiple imputation method based on finite population Bayesian bootstrap, proposing a doubly robust approach by extending the standard multiple imputation and integrating the machine learning techniques with the currently used handling missing data methods. These are some of the references I use. I would like to thank the Stellenbosch University for the financial support during my master's program and to conduct this particular project as well. Thank you so much. Over to you, Peter.
Thank you so much, Darif. So well done. And that was approximately 15 minutes. I did not hit the timer the moment you began, so we were estimating there, but very good. We do have a moment for questions if necessary, but I don't currently see any in the chat, and I will double check the Q&A. And I am not seeing anything at the moment. So we will keep an eye on the chat and the question and answer feature throughout this session. And what I would say is, if you have a question for Daripsa a bit later in the program, please just mention in the chat who your question is for, and we'll make sure it's addressed if there's time. Okay, thank you, Daripsa. Appreciate it very much.
Thank you so much, Peter.
Yes. And it's not the same as being in Atlanta, but we're glad you were here today. So I'd now like to say, we have one quick question. Let's see from, all right. Okay, in the interest of time, let's see, I'll allow you to ask your question just by voice. Aringa, yes, would you like to speak?
Can you hear me?
Yes, thank you.
Okay, I'm Direnya, and thank you, Teresa, for your nice presentation. I know you before when we done our masters together. Since then, I'm really very happy for your successful. I have questions today on your presentation that did you try to apply some generalized linear models for the same thing for missing invitations? So I want to know if you have tried such generalized linear model because they are very important for this missing data, especially in Bayesian applications. So that is my question. Thank you.
Daribsa, are you able to respond? Please feel free.
Yeah. Thank you so much, Grenya, for your nice question. So in our case, we actually used like the 5 approaches I mentioned. So for like the 5 different methods, we use 5 different methods of handling missing data. And in order to pull like the results from, or like for the final parameter estimate, we again used different methods. For example, like survey logistic regression and the mixed effects logistic regression in the case of the heteroscedastic multi-level multiple imputation approach, and so forth. So the methods are like complete case analysis, inverse probability weighting, and the standard multiple imputation, and the mixed effects, the heteroscedastic multi-level multiple imputation. So we haven't tried the approach you mentioned in our case.
Okay, thank you very much. That is what I was asking. Yes, thank you.
Okay. Peter, I think you are muted.
I absolutely am. Yes. Thank you for that. There's one other question which is in the question and answer feature, but we do need to move on to our next panelist. So may I just ask, are you able to see that question? And if so, would you be able to answer that in writing?
Okay, yeah, I will respond to that question. Yeah, I will respond in the text. Yeah. Thank
Okay,
you.
very good. Great. Thank you. I would like to keep us relatively on schedule. So, hello, Hawa Nabaya, am I saying that correctly?
Yeah, it's okay.
Okay. All right. Very good. Welcome. Thank you for being speaker number 2 and for joining us. Would you like to test your screen? You should be able to share now.
Okay, let me try to share it and see.
Mm-hmm.
So are you able to see my screen?
Looks like it's coming up. Yes, we can see it.
All right.
Very good. You might want to put that in slideshow mode, but apart from that, everything looks good.
Okay. So good afternoon, everyone. Good morning, everyone. To those sides, to our side, it's good afternoon. I think to other sides, it is still morning. First and foremost, I'm very delighted to be among the finalists of Florence Nightingale Award. And my name is Hawa Nabaja from Makerere University School of Public Health. I would also appreciate everyone who has managed to log on. And my special thanks goes to the people who are managing and coordinating this award for giving us opportunity to present our work. I'm going to be presenting my paper titled Using Machine Learning to Develop a Cervical Cancer Prognostic Model Predicting Survival Outcomes Among Ugandan Women. we all know that cervical cancer, it is the cervix of the, it is the cancer of the cervix, whereby abdominal cells start to grow on the cervix. It is the fourth most common cancer among women, whereby it is there is an estimate of over 600,000 women who die, 600,000 women who die due to this disease, and over 300,000 women are also said to die of this disease. When you come to Uganda, about 6,000 women are diagnosed of cervical cancer every day. I mean, every year, and about 4,000 die due to this disease. And about 61% of the women die of cancer-related, who die of any cancer-related due to cervical cancer. This is causing a worry and a significant health problem to Uganda. However, the public of Uganda has tried to implement or to improve, to take an initiative to improve on cervical cancer management, whereby it has started on cervical cancer screening, HPV vaccination of children, of girls under the age of 15, then also carrying out sensitization program. The clinicians in Uganda tend to use what they call the tumor staging systems. These systems are composed of what they call the laboratory variables, which are barely understood by the patients or the caregivers. So most of the patients end up missing out on their prognosis. That's why we have high rates of mortality, high loss of follow-ups, maybe to cervical cancer treatments. That's why when I wake up, I said, no, what if I use machine learning algorithm where because of these models being capable of accounting for the heterogeneity between the tumor staging and also patient outcomes. So this, when I go to study methodology, you look at this study was carried out at Uganda Cancer Institute, because it's the only institute that has the mandate to carry out any cancer-related research or treatment or diagnosis. It is this was a retrospective cohort study whereby patients following cervical cancer treatment at the UCI, that is Uganda Cancer Institute, between the year 2015 to 2020 were considered. I considered this year, this study period, because it comprises of the 3 seasonal scenarios that Uganda faced. The first scenario was before the breakdown of the radiotherapy machine at UCI. Then the second scenario, when the machine broke down, and the third, for over even 6 months, patients were not receiving any treatment. Then the third one is when we had the breakout of coronavirus. Records of women between age 15 to 69 were women between age 15 to 69 were considered because at the age of 15, it is believed that the incidences of cancer, cervical cancer, start to manifest, and that due to active sexual intercourse, and at the age of 70 or 69 and above, that's when there is low incidences of cervical cancer due to low or inactive sexual intercourse. I thought approval from ethical committees of UCI and MAC-SPH, that is Mackay University School of Public Health. Then there was no specific sampling method. Sample size was based on the literature by Doza, that paper, although other authors suggested different methods such as post hoc method, power analysis, but these ones were limited on ground due to the lack on my side of the data set that I can use to fit the learning curve. Other authors also suggested the use of standard mean differences, effect size, and statistical power. Still, these ones were limited on my side due to miscalculation and lack of experimental processes. Then when I come to my outcome, the outcome variable was death due to cervical cancer. So survival time was measured in months. My independent variables composed of both the demographic variables, and these included age, BMI, and so on. Then the clinical pathological variables included histological type, histological grade, tumor sites, among others. Data was extracted using a tool which was designed in REDCap. And since UCI had not gone 100% electronic, some information was supposed to be extracted manually by identifying which variables have which missing information. So after that, I did data management, and missing data was handled using MICE, multiple imputation shade by shade equations, and also KNN, k-nearest neighborhood. The analysis was carried out using 3 phases. The first phase was variable selection, whereby descriptive analysis was carried out, then bivariate. Then for model the second phase was model development, where multivariable analysis was carried out using both the traditional statistical methods such as the Caucus proportional hazard, and also the logistic model diagnostics were done also. The best model was chosen using the KII and the BIC. Using the AIC and the BIC. Then the mount correlation was also tested using the correlation matrix. Then for probabilistic neural network was considered among all the neural networks due to its capabilities of handling complex data and also being good when you have small sample sizes. The model at a later stage, then the third step was model validation, where k-fold validation was done using 5 folds, and then other performance metrics such as sensitivity, specificity, among others, were considered. And then at the end of the day, this is the analysis. I ended up with 500 patients being screened. Then 55 were excluded and 39 were screen failures. At the analysis level, my sample size was 413 patients, whereby the data set was divided into 60% training set and 40% the test set. So this is the descriptive, whereby you see that most of the patients had missing data on the body mass index. Then when you look at 88% of the, actually 53% of the patients were HIV negative. Then the age at diagnosis, you find that between the age of 59 to 69, most of the patients were aged between those categories. When you go to histological type, the most common stage was stage 3. And when you look at the histological grade, most of the patients had poorly differentiated grade, and so on and so forth. So at the end of the day, you look at what was the vital status of my patient. You find that 45% of the patient had died, whereas 42% had gone, they couldn't be traced, so they were lost to follow up, and only 13% were still alive. So you see how there is a burden of loss to follow up, and also the high mortality rates due to cervical cancer. So the overall survival estimates for all patients using Kaplan-Meier method, you find 36.5% of the patients surviving for that period. Then when we consider, since most of the treatment or the predictions that are made currently are based on FIGO staging, you find that even people who present with late stages, that is stage 3 and 4, die earlier than those ones with stage 1 and stage 2. So when we go to model development, remember we developed the model using both the traditional methods and also the machine learning method, that is the PNN, the probabilistic neural network. You see that people from Eastern Uganda had a high, maybe we can say the risk of them dying due to cervical cancer were high among the Eastern women coming from the Eastern region. So also the odds of someone not surviving not surviving cervical cancer were still higher when we use the logistic. Still, when you go to the grades, you find that actually here, the women with the grade 2 had a higher risk of surviving cervical cancer compared to those with grade 4, and so on and so forth. So still, when we continue, you find that even women who presented with stage 3, they had a higher chance of a higher risk of dying due to cervical cancer compared to those who had maybe stage 2. Okay, so even the odds, even in the odds, you find that someone surviving cervical cancer were much more lower in stage 3 compared to those with maybe stage 1. So when we go to probabilistic neural network, this is the network that has 4 layers. The first layer, it is the input layer. The second layer is the pattern layer. The third layer is the summation layer. And then we have the decision layer. So this layer feeds the input layer, it feeds the pattern layer with the information, which now I feed all the identified prognostic or the identified predictive variables. Then at the end of the day, each would decide either someone would survive or would not survive. The only limitation that I faced was to assess the contribution of each factor to the model, which was a limitation acknowledged. I couldn't because of the black box of machine, the black box limitation. So when you go to model validation, you find that the PNN model was really performing well. That is the probabilistic neural networks on the training set still. You see its recall decision, it is 78%. When you go to sensitivity, it is 77%. And the F-score also, all the metrics were good. So still, when you go to evaluating it, then when we validated the model using still the test set, you find that the ROC curve was about 0.72, which was not.
Oh, we may have lost our
Yeah.
analyst. Hold on. Let's see here. These things do happen. All right. You're back. Hello.
Yes. Sorry about that. It's my network. It's threatening to rain this side.
Oh boy. Okay. All right.
So
Well, very good.
Can I continue?
Yeah, I can give you one extra minute here. Sorry about that. Okay.
Okay. All right. Thank you so much. Let me try to summarize. Okay. So when you go to
Let's see. It looks like it's coming up just slowly.
Okay, so when you go ahead and look still, when you compare the model using the training set and also the test set, still the model is performing well. I went ahead and also compared the PNN model with the traditional model, which performed better, and that was logistic regression model. You see that when you look at the metrics or the performance metrics, still the PNN model outperformed not so much, but at least it outperformed the logistic model, maybe because of the sample size being small. That's why even the logistic model was performing well. Then this shows the confusion matrix whereby you could see how many were identified, the true positives, how many those ones who died and they really died, the true negatives, the false negatives. For the PNN, you see there are 3. For false negative, there are just 20. For the logistic regression, you see that the true negatives are 40, then the false negatives are, the true positives are 40 and the false negatives are 6. Then you go ahead, you can calculate and still you end up with these specific metrics. So my recommendations would go to, my discussion shows that this study identified that it would work better if they incorporate in both the patient characteristics and also the when you're trying to predict the patient prognosis, or you're trying to determine the patient prognosis, it would be better to use both the demographic characteristics and also the clinical pathological characteristics, not only the pathological characteristics as currently being done at Uganda Institute. So I would recommend also that they do this study in I would recommend also that they do a prospective study with an increased sample size, while focusing on putting a critical eye on loss to follow-up, because it really affected my result, which I can acknowledge as a limitation, and I didn't try to analyze what caused maybe the higher rates of loss to follow-up. Maybe sensitivity analysis would work better, but I didn't do, which I acknowledge as a limitation. Thank you all for listening to me.
Well done, and thank you for braving the elements. So sorry that happened, but you know, it's not, the technology is wonderful, but it's not perfect. I will, because of the time, I will ask those who may have questions to use the Q&A feature. I see that the other questions that were provided earlier, they are being answered now. And so we're going to move on to our next presenter. And may I ask, Kaptamu, are you ready to test your system and share your slides? Let's see, trying to promote them to panelists so that they can speak. But if not, I would ask that Ulrich Kemo Safak, if you are ready to go, I'm going to promote you to panelist as well, just to keep things moving. And I've attempted to promote you to panelist. Let's see, Ulrich, can you hear me, please?
I can hear you. Can you hear me?
Yes, yes, very good. Okay, welcome.
Thank you. Can you see my slide?
Not yet, but go ahead and try. I'll make sure that you are a co-host so that you can share.
Oh, so I need to put my video to...
Yes.
Do you
Yes,
see me?
now we see you. Hello. Good
Okay,
afternoon.
great.
Very good. And you should have full access to share your slides now. So if you'd like to try that.
Can you see my slide? No?
Not yet.
Okay, maybe I need to click on
You
share.
should see a green button at the bottom of the screen if your interface is like mine.
Okay. Screen and then share.
I think it's working.
You see my slide?
Yes, I can. And Hawa, I will just mention that a question has been dropped in for you in the chat, so you can look for that. Okay, but yes, Ulrich, thank you very much for speaking today. You are number 3, and maybe lucky number 3, who knows? So I appreciate your attention to the presentation. And again, because of timing, I would ask that everyone share their questions at the end. But please, the floor is yours.
Okay. So you can see my full screen, right?
I can, yes.
Okay, great. So yeah, thank you, Peter, for the nice introduction. Welcome everybody to my presentation entitled Tri-Level Variable Selection Method for Ultra-High Dimensional Multiomic Data. So this project is part of my thesis from New Mexico Medical College of Wisconsin. So the highlight of this presentation is simple. After the introduction, I will introduce a proposed method, and then I will share simulation studies as well as real data analysis, and then I will end the presentation. So our project is motivated by the fact that investigators often want to use multiomic data to identify genes and omics that are related to an outcome variable that can be disease like cancer. And the multi-omic data has two specifics. First, that is ultra high dimensional, meaning that the number of variables is much more larger compared to the sample size. And the second one is that it has hierarchical structure data, as you can see here in figure 1. So you have 3 samples with 8 covariates, and you have 2 omics, RNA and proteins. So you see that RNA 1 and proteins 1 that are coming from the same genes are likely to be correlated because proteins is the result from this translation of RNA. And also gene 1 and gene 2 that belongs to the same pathway are also likely to be correlated. So pathway, roughly speaking, are genes which activity aim to the same function. So they are likely to be correlated. So in this way, we have a tri-level hierarchical structure. First, the group structure, which is made of pathway, and then the subgroup structure, which is made of genes, and then the individual structure, what that means, which is made of omics. So auto-omic data has 2 issues. The first one is that we cannot rely on pathway. Why? Because first, we have multiple sources of pathway, like Keck database and Reactome database, and it's unclear which one to trust. And the second reason is that the pathway overlaps. And the third one is that sometimes in the data, we can see 2 genes in the same pathway that shows a weak correlation, when you can see 2 genes in different pathway that show strong correlation, which is not good. And the second issue is that the existing penalized regression will be unstable or inefficient when we are dealing with ultra-high dimensional data. So in the background, when you have ultra-high dimensional data, the literature recommend to first do the screening. Screening means that you're going to reduce the number of covariates such that it becomes less than the sample size. And when you reduce that without losing important covariate. And after the screening process, we're going to use now existing penalized regression because the sample size now is now larger than the number of covariate. And it's, in the literature, we have a bunch of screening methods that run from the marginal screening and the joint screening and the group joint screening. But unfortunately, we don't have a screening method that consider ultra-high dimensional, the hierarchical structure of the data. So what you propose is a tri-level variable selection method that has 3 steps. The first one, we're gonna cluster the genes instead of using the existing pathway. And the secondly, we're proposing a screening method that considers hierarchical structure of the data. And the third step is to use the Goodbridge regression to implement the variable selection. So in the clustering, we recently published a paper of a clustering method called MMAGC, which is that clusters the gene based on the correlation of the genes. So here we are using the canonical correlation to do the correlation between 2 genes. With multi-omic data, the correlation between 2 genes, the correlation between 2 matrices. And we use the canonical correlation to do that. So basically, to get the canonical correlation, we're going to do a linear combination between RNA1 and protein 1, you get in 1 vector. And then you do linear combination with RNA2 and protein 2, you get another vector. And the correlation between those 2 resulting vectors give you 1 correlation, right? And we do the process again and again while changing the coefficient of the linear combination. And the process, the maximum correlation getting out of this process is called the canonical correlation. So after getting the correlation between the gene correlation, then we're going to use the modified WGCNA and the hierarchical clustering to get the cluster. So I will not focus more on this step. So if you have questions, I'm going to come back for the sake of time. So the screening method that we propose is based on generalized linear model, given equation 1. So where f is the link function, yi is the outcome variable, beta is the regression parameter, and xi is the covariate vector, n is the sample size. So we here this for the I individual. And we assume that we have p covariates that are grouped into capital C disjoint clusters. And those clusters are indexed by A1 to AC, which is a partition of 1 to P. So without loss of the generality, we can assume that the regression parameter are stacked in order. So first we have the regression parameter for the first clusters, and you have the regression parameter for the second cluster, and so on. So you assume that you have capital G number of genes. So what we want to do is to maximize the likelihood, given that the number of clusters is less than Q1, and for each cluster C, the number of genes in that cluster should be less than Q2C. So here Q1 and Q2Cs are pre-specified constant. And because the number of covariates is very large compared to the sample size, this equation 2 is not solvable. But when we want to do the approach that we took is that we want to we are going to approximate the log likelihood given in equation 3. So this function is nothing but the second order Taylor expansion of the log likelihood with 2 modifications. So first we have U here, which is a pre-specified constant, and W here, this matrix is a block diagonal of the gene-based block diagonal of the information matrix. So now by doing this approximation and replacing the likelihood with this approximation, guess what? That equation now has a solution, but not only does it have a solution, that solution also have a closed form. And we're going to use that closed form to iteratively update the value of beta as given here in this algorithm. And we're going to iteratively update the value of beta until convergence. The algorithm is pretty simple. And with this algorithm, we mathematically show that our method has a short screening property, means that it retains all important genes with probability 1 as n increases, so, with p still being greater than n. So in the third step, we use the group bridge regression to do the variable selection, because lasso and group lasso, you can see it selects either important group or important individual, but we use the group bridge regression because you can select both the group and the individual, and it has a tuning parameter lambda that we can use the Bayesian information criterion to estimate it or the cross validation. So we did some simulation. So we simulated a 3-omic data using the multivariate normal distribution with mean 0. We consider 4 types of correlation, illustrated here in figure 2. The correlation between 2 genes, 2 omics in the same genes, tau 1. The correlation between the 2 omics of the same type from genes in the same cluster, tau 2. The correlation between the omics of different type from genes in the same cluster, tau 3, and the between cluster correlation, tau 4. And we consider 2 scenarios when tau 1 is greater than tau 2, and then when tau 1 is less than tau 2. So we consider 4 important clusters, 1 cluster of size 5 with 1 important gene, 1 cluster of 10 with 1 important gene, 1 cluster of size 20 with 1 important gene, and 1 cluster of size 40 with 2 important genes. So in total, we have 5 important genes to be able to select. And the outcome variable was binary using the Bernoulli distribution. And we considered 3 sample sizes, 200, 400, and 800. And P, the number of covariate, the number of genes, and the number of clusters were accordingly increased. And we set Q1 to be 8 and the Q2C to be 10% of the cluster size. We set U to 10 to the 5. You can see why it's very large, right? So actually, when showing the short screening property, we show that the condition on U is that U should be greater than the largest eigenvalue of a giant matrix. So that's why we put it like very large to be sure that it's going to be greater. So we evaluate the performance of the method compared to the gene-based marginal method and the omic-based marginal method. And also we want to also compare it with the proposed method when instead of using the block diagonal as showed previously, we're going to use the diagonal of the matrix. So what we reported is the adjusted rand index between the 2 clusters and the true cluster and the predicted clusters. And we also reported the proportion that all important genes were selected, the average proportion that important genes are retained. So these are the results for the first scenario. So first, adjusted random index of 1 means that our method was able to perfectly identify the cluster, which is nice. And this here we have the performance when we have 800 samples and 900 covariate, 300 genes, and 22 clusters. You will see that the marginal omic regression is able to retain all important genes 29.5% of time. The gene marginal screening retains all important genes 12.5% of time. The proposed method with the diagonal matrix retains all important genes 39% of time. And the proposed method with the block diagonal retains all important genes with 33.5% of time, which is great. And you will see that the omic marginal screening method retains averagely 79% of important genes. The gene marginal method retains 70% of important genes. The proposed method with the diagonal retains 85% of genes. And the proposed method with the block diagonal retains 82% of genes, which is great. So now, as the sample size increase, you will see here with 400 samples, 1,680 covariates, 560 genes, 42 clusters, you will see that the proposed method now have greatest value, which is great. So the similar result were also observed in scenario 2. And for the sake of time, we will not show that here. So we also wanted to evaluate the method when the clusters are not well identified. So we randomly permuted 16% of genes, and the results, the cluster of 60% of genes, and the result are shown here. As previously, you will see that when the sample size is small, the proposed method performs like similarly compared to the other one. But when the sample size increase now, you will see that the proposed method performs best. And also you will see that all the method here, the performance of all the method here are relatively lower compared to the performance when the clusters are well identified. And also similar result were observed in scenario 2. So we apply our method to the human breast cancer that was downloaded to the TCGA website, and the aim was to identify the genes that are significantly related to the breast cancer. We have two types of omics, the RNA sequencing counts and the DNA methylation beta value, and we coded as 0 as stage 1, 1A, 1B, 2, 2A, and 2B, which is the stage of the disease, and 1 as stage 3 and above. So after the preprocessing step, we end up with 308 samples with 1,894 covariates. So these are the results of the real data analysis. It's a heat map. So here we have the genes and the omics. So, and here we have the variable selection method. So a black square in front of gene means that the omic was selected by the method, and a white square means the omic wasn't selected by the method. So in blue here, we have the genes that are claimed by the literature to be related to breast cancer. In black, you have the genes claimed by the literature to be related to other type of cancer. And in red are the genes that are not yet claimed by the literature to be related to cancer. So the take-home message here is that first, the variable selection method that we the proposed method means only 3 cancer genes when the other method means more than 5 cancer genes. So the other take-home message is that if you only consider, instead of variable selection, you only consider the screening method, the proposed method failed to retain 2 genes, important genes, when the other method seemed to retain 2 and above. And more interestingly, our method were able to select 3 genes that are not yet claimed to be related to the cancer. And also the other method did the same. So, which is like a red flag saying that these genes are potential breast cancer related. So to evaluate the performance of the method, we did the 5-fold cross-validation 20 times. So that helped us to compute the testing AUC with 1 float, and 4 float was for the training. And you will see here that the AUC are kind of similar, even though the proposed method has a slightly higher AUC, even with a smaller sample size, a smaller number of genes selected. So to conclude the presentation, we can see that we propose a 2-step variable selection method for ultra-high dimensional multi-omic data. The simulation method, simulation studies show that our method performs well with compared to its competitor. And the method performs better when the clusters are well identified. And when they are not well identified, you need more sample size to perform as better as well as they perform when they are well identified. And also we applied our method to the breast cancer TCGA database, and we were able to identify 3 potential gene cancer genes. So these are the reference of presentation. I would like to thank my advisors, Dr. Lin, Dr. Ann, for their guidance and support, and also thank you guys for your kind attention. Thank you.
All right, well done, Ulrich. Let's see. Yeah, very well done and right on time. So thank you very much.
Thank you.
We have one question, and as I try to connect our final speaker, let me see. Okay. Mariana, I'm allowing you to speak if you have a question.
Oh, hi, Peter. No, I don't have a question. Did I press something wrongly? Sorry.
Oh,
Yeah, your hands up.
I think you raised your hand, so
Oh, no, my hand is, sorry, Peter, my hand is raised since I could not speak from the beginning. Sorry.
not a problem. Okay, thank you.
Yeah.
Very good. Well, so we have one final speaker, and as you may have read in the chat, we will extend this session a bit longer. I would also ask those of you who have a question for Ulrich regarding his presentation, please include your question at this point in the chat. I think it would be useful for the audience to see the question, and Ulrich, you are able to respond right there.
Yes.
And any questions that we receive following the session, we will relay to you and share with the audience. And we are also recording this session, as you know. So, so thank you very much for your presentation. Very well done. And now I believe in the queue we have our final presenter of the day, Haptamu Tilaye Wubete. And I hope that I said that correctly. Can you hear me?
Yes, yes.
Okay. All right. Very good. Welcome.
Prof. Peter.
Yes. Nice to see you. Why don't we try your slides and see if we can see those in the audience?
Okay, okay. Thank you.
Sure.
Here it is. Is it visible?
They are coming up now.
Okay.
Ah, yes. Now we can see them. Very
Awesome.
Okay. Let's see. Well, so I think I will just leave it to you now. You are the fourth speaker today. So thank you very much for coming on, and you may give your talk.
Okay, thank you. Good afternoon.
Yeah.
Dear organizers and attendants, my name is Haptamu Tilaye from Ethiopia. Currently, I am a PhD student in Bahar Dar University. And I want to thank you giving me this opportunity to present my work entitled Spatiotemporal Modeling of Household Food Insecurity Levels in Ethiopia in IBS Florence Nightingale Memory Award Conference. Here are the outlines. The outline include introduction, method, result, conclusion, and finally contribution, limitation, and future works. When it comes to the introduction of food insecurity has been frequently occurring problem in most parts of Ethiopia due to culture, natural and man-made shocks. The problems are chronic food insecurity and vulnerability. Those households affected by these problems take less food comparing to secured households, as Food and Nation reported. Particularly, chronic food insecure households are those suffered in severe food shortage, which can result to malnutrition, as Maxwell 1999 When we come to, again, on the background of food insecurity, it got its attention after World Food Crisis of the 1972-74 and African famine of 1984-85, as Maxwell and Frank Berger. Food insecurity is, as you know, it's a chronically increasing worldwide problem due to limited resources and aggravated by global wars like trade war and those actual real wars and pandemics like COVID. Globally, slow rise starts in 2040 with 8% and continued slowly out to 2019, and it reaches 9.9%, but inflated after COVID-19 to 12% by 2020, as UNICEF reports. This challenges FAO plan to end food insecurity by 2030, and this shocks mainly impact developing nations like Ethiopia. When you come to Ethiopian food insecurity status, it is grappled with frequent food insecurity. For example, the famine of 1979 and 80, and the famine of 1995-96, as Devarex and Sussex indicates by 2000. And the other one is a food shortage due to 2015 El Nino drought, as let's say it indicates by 2020. And recently, more than half of the population face food insecurity for a year 2090 to 2021, as Berkeley indicators. And it have an adverse effect on health, like it complicates mental health, child malnutrition, woman anemia, and type 2 diabetes, as World Food Programme reports. In addition, it also affects the economy, which resulted to low human development, such as poverty and inequality, as Garton it indicates 2010. From literature, we find gaps and previous study in the country are case or cross-sectional studies, which only show the spatial distribution or the effect of some factors like socioeconomic, demographic, or other some factors. And the assessment of food insecurity were not adjusted for diverse feeding culture or pattern effects. And also this temporal challenge of geographically wider problem has not been well investigated in Ethiopia. Therefore, as an objective, we just want to assess the feeding culture corrected food insecurity level of household spatiotemporal change by accounting for the effect of comprehensive factors. And the data is, we take the data from Ethiopian Socioeconomic Survey Panel data with a sample size of 3,835 households for 3 consecutive years. It is a longitudinal data from a year 2012, 14, and 16. And the study area is an administrative zone, as the figure indicates here. And we just input missing values using longitudinal mean, since it is a longitudinal data, and mean imputation and regression method based on the position of missing values. And the missing values is around 8% in total. The response variable is an ordinal response. It is labeled by data-driven approach using longitudinal quantile regression that is published at Frontiers by Ubate and Detail in 2023. And we classify the food consumption score into 3 categories as food insecure, vulnerable, and food secured. And this food secured score is calculated first using World Food Programme formula, that is the sum of the frequency, that's the number of days a food is eaten per a week in a household, multiplied by the weight that's given based on the nutritional importance of the food. When you come to the modeling part, spatiotemporal model is applied, and here we assess the spatial and temporal pattern as well as the interaction by considering nonlinear and linear effects. We do this to borrow information from neighbors and temporal pattern. As I have stated before, food consumption score level is an ordinal, and we model it using a cumulative probability model, since the latent variable is continuous and it is a truncated normal. And the modeling is given here. The CDF for the ordinal is equivalently expressed by the CDF of the continuous response, and it is equivalently expressed by the CDF of the residual, which is a function of the linear predictor and the cutoff point, where the linear predictor is estimated by using Knorr and Held formula as given here. That is the sums of the linear part, the nonlinear part, the spatial part, and the temporal part. And we extend this main effect model, spatial-temporal main effect model, to add the space-time interaction effect to account the separability of space and time. And the model is given here. And we use the Concord product to fit the covariance structure for this space-time interaction. And we have 4 possible covariance structure. That is, the first one is type 1, both space and time are random, have random pair. And for type 2, space and when space have random, but time have random, when time have structured, that is estimated by random of 1. In type 3, space is estimated by Markov random field, or using two-dimensional random of 1, and time is estimated by with a random pair. And in type 4, both space and time are considered as structured. It is a true inseparable model. And using this 4 possible model and main effect, we estimate around 10 models. Here is model development. The linear effects are estimated using linear regression, using maximum likelihood estimate, where by taking the coefficients pair as diffuse or constant, and then linear effects all linear effects are fitted by cubic splitting, as given here, where its coefficient is estimated have a random of 2 pair, and spatial effects are modeled by splitting into 2, structured and unstructured, to account the structurally affecting and locally affecting unknown covariates on the food insecurity here. So therefore, the structured part is estimated by using Markov random field pair and bivariate p-spline pairs. And here is a Markov pair formula, and the unstructured part is estimated by Gaussian pair. When you come to the temporal effect is fitted by random of 1 pair, as given here, and the unstructured part is estimated using Gaussian pair. But for the case of spatial matrix, when we have spatial matrix giving with longitude and latitude, the spatial weight matrix is estimated using the Euclidean distance. In that case, we should estimate the surface. Therefore, the Concord product have faced difficulty in estimating this surface. Therefore, we approximate the Concord product using the tensor product. That is a product of 2-dimensional p-spline and 1-dimensional p-spline. 2-dimensional p-spline for space and 1-dimensional p-spline for time. Therefore, the interaction effect for type 4, this one is estimated using a tensor product of 2-dimensional random of 1 and 1-dimensional random of 1 is given here. And the pairs are given here, as you have seen here. It is just approximately normal with mean taking from its neighbor and variance proportional to the number of neighbors. When we come to the posterior model, the posterior model is given here, spatial temporal empirical bias interaction effect model. This posterior model is the product of the likelihood, the non-linear pairs, the spatial pair, the temporal pair, the space-time pair, the linear pair, the pair for linear, and the pair for the variance. The estimation technique we use is empirical bias for fast convergence and Ramal for minimum variance for in the random effect, since it uses Gauss-Markov. And we model, and after model, we compare using GCV. Around 10 models are compared here, 5 for contingency neighborhood method, and 5 for Euclidean distance neighborhood method. Based on GCV, type 3, Markov random field brings a smaller GCV, and the interpretation or the inference is based on this model. We select type 3 interaction effect with Markov random field pair as a best model. Sorry. And the result indicates that here the linear effects showed that urbanization, education, farm type, employment, fertilizer have a significantly decreasing effect on severity of food insecurity, whereas land ownership and shock have a significantly increasing effect on severity of food insecurity. But when we come to the nonlinear effects, as you have seen here from the graph, a household having a non-agricultural business have its food insecurity is declined, but for those households having more than 3, the food insecurity declines faster. And again, the dependency ratio in the household have an increasing effect, but up to 4, it have an increasing effect, but after that, the effect is complicated or difficult to interpret here. When it comes to the drinking water effect on food insecurity, having the drinking water source have a declining effect on, or it decreases food insecurity, as I've seen here, more than 1 have decreased food insecurity, but have no source have an increasing effect on food security. Similarly, on sanitation, household have better sanitation, have better food insecurity, or it declines food insecurity. Moreover, here coping strategy index, higher value of coping strategy index, soil property, and agroecology decreases food insecurity, whereas higher amount of rainfall that may be due to erosion and workability of soil and rooting condition of soil, it have increased the food insecurity, as I've seen here. From the observed value of food consumption, food insecurity levels, as we have seen, there is a spatial correlation on both years. As we have seen, the northern and southwestern part have suffered with food insecurity, whereas the southern eastern is better. Temporally, if you see, it declines in both sides. The red becomes more blue and gray. Therefore, we can see that from this observed value, there is a spatial correlation and temporal, spatial dependency and temporal dependency. Therefore, based on this observed value suggestion, yes, Peter.
Yes, I am sorry, Haptim. We are at the 15-minute mark. Perhaps you can finish explaining the slide that we are on, and then we can take a brief moment for questions. But yeah, please.
Okay. I'm just in conclusion. Okay, I'm going there.
Sure.
I'm already there. Okay. Thank you, Prof. And from this, we just model, and the model indicates that, as I've seen, the main effect indicators there is a higher food insecurity on the northern and southwestern part, and food security is better on the southern and eastern. And based on comparing relative to this main effect model. The type 3 indicates that by comparing these two plots, this shows the severity. The severity is high on the northern to the eastern part, but it is not changed on the middle. But again, the severity declines on the southern eastern part. Therefore, the food insecurity on the northern becomes severe on the, and the food insecurity on the southeastern becomes remains unchanged. Whereas the food secured status, the better food secured status on the southern eastern becomes better, whereas on the central, the vulnerability becomes the same. And again, on space-time interaction, we see that as time goes, the food security declines for all zones. Therefore, we can conclude that the household living in neighboring zones share similar food insecurity level, which showed slight decline over time trend. Hence, working on urbanization, education, employment, non-agricultural business by controlling shocks, small land ownership, and dependence ratio can reduce food insecurity. And the contribution here is we just found an innovative comprehensive statistical methodology to determine household food insecurity. And again, we find standardized leveling of severity that accounts local factors that feeding culture. And the limitation is data is limited in certain time points, and some zones are data are not included. Therefore, on the future, one can capture spatial-temporal dynamics in better by accounting confounding factors and sample zones and more temporal data. Thank you. Thank you, Prof. Peter.
Thank you very much, and very well done. I apologize that we don't have a bit extra time. One of the challenges with a Zoom system is that we can't all meet outside for a few minutes after for a coffee to dig a bit deeper into these talks, and I wish we could. But this is very useful. I will ask all of our speakers today to consider whether we might be able to share a copy of their slides with the audience following this session. I'll be in touch with you over email regarding that. It is up to you, certainly. But I'd like to thank Daripsa Bedada, Hawa Nabaya, Ulrich Kemo Safak, and Haptamu Wubete for joining us today, our first 4 Florence Nightingale finalists. We do have one additional session that we are tentatively scheduling for February 18th. There will be more information shared regarding that session shortly. If you have any questions for the panelists that you weren't able to share during the session today, please send a message to me directly. It's pdoherty@biometricsociety.org, and I will be happy to connect you with the speakers and forward those questions along. But I hope you've enjoyed this session. Once again, it's not like being in Atlanta, but it is what it is. So I appreciate the technology. Thanks to all of you for joining us, and we will see you next time. Take care. You may now disconnect from the. Thank you. Thank you. Thank you to all the panelists and our judges, by the way, and our chair, Sheely Lin. Thank you all.
Thank you.
Okay, thank you.
Thank you, Prof. Thank you so much.
Take care.
Thank you.
Bye-bye.
Bye-bye.